All right, so today we're putting the last two steps into our process for predicting products with double displacement reactions. So all those steps are written on the worksheet that I gave you guys. I have outlined here the three that we learned yesterday. So we're just adding steps 4 and 5 into things. So we're going to just jump right into the example, and then I'll explain a couple things as we go. So in this example, we have silver nitrate reacting with sodium phosphate. Those are both aqueous. And that's going to always be true with double displacement reactions. We're always going to have two aqueous compounds, okay, on the left side. That is the reactant side of the equation. So step 1 we learned yesterday is to switch the dance partners up. So that is going to be silver and phosphate on this side. And we don't yet know the state of matter, but I'm going to put some parentheses there for that. And it's also going to be sodium nitrate. And we don't yet know the state of that matter. So that's step 1, switching the dance partners. Any questions about that before I go on to step 2? Okay. Step 2 is to neutralize the new compounds. And silver has a +1 charge, phosphate has a -3 charge. So what do I need to do there? Question mark. Need to put a 3 subscript next to the silver. Okay. Now we have a neutral compound. Over here, we've got a +1 and a -1, so that is already neutral. We don't need to do anything to it. So using subscripts, I just neutralize the new compounds. We're done with step 2. Step 3 is to now balance the equation. You can use these tables that I made for you, or if you're able to do it just by looking at the equation, you can do that. So when I look at this, the first thing I noticed is I've got 3 silver on the right, and I only have 1 on the left, so I'm going to put a 3 there in that place. Of course, I might end up having to change that. That's okay, but currently my silvers are balanced. And I have 3 nitrates on the left, and I only have 1 on the right, so I'm going to put a 3 there also. That balances my nitrates. That also gives me 3 sodiums on the right. And I have 3 on the left already, so those are balanced. And lastly, I've got 1 phosphate on the left, and I have 1 phosphate on the right. So everything looks balanced. You can check those off if you're using your table. So we just finished step 3. Everything I just did is what we learned yesterday, so no new stuff yet. Questions, though? Okay, moving on. Now we are going to look at our products, silver phosphate and sodium nitrate, and we are going to ask ourselves what state of matter those are. Are they solid or are they aqueous? And we're going to answer that question by going to our solubility tables, which can be found on the back of your periodic tables in the upper right-hand corner, as you look at them right here. So I'm going to write those compounds down. We have silver phosphate, was it? Okay. Silver phosphate. And we have, what was my other one? Sodium nitrate. Okay. All right, so this is a little confusing at first, but once you get it, it's pretty easy to navigate this table. So let's look at it here. We have 4 parts. Everything in this box is going to be soluble. That means it dissolves in water. So the compounds dissolve in water. And the way we're going to say that is aqueous. We're going to put an AQ in parentheses. Okay, everything in this box down here is insoluble, which means during the reaction, the compound is going to form a solid. And the way that we show that is with a downward arrow in parentheses. And again, that means forms a solid during the reaction. The other word for that is a precipitate. So what that would look like, and we're going to do an experiment on Monday with this, is you mix two liquids together and you'll start to see a powder in there. That is the precipitate forming a solid. Mainly, we're going to start on just the left-hand side of the table. That's the main side of the table that we focus on. The right side of the table is just for exceptions. And we use a different color here. This corner is, again, insoluble. So this is going to be solids, where we use the downward arrow. And the lower right-hand corner is soluble, which again means dissolved in water. So we're going to use aqueous for anything found in that box. So let's do an example. Let's look for silver phosphate first. I'm going to clear all this ink I've got on the page. So I'm going to begin by just scanning for either silver or phosphate on the left side of this table here, okay? Again, I'm talking about silver phosphate and sodium nitrate. And I'm going to look for either silver, Ag, or phosphate over here. It doesn't matter which one I find. Either one of them will tell me the same thing. They will agree with each other. They'll never contradict each other. So as I scan down the left side here, I see a phosphate right here. And it's in the insoluble section. So that means generally phosphates are going to be insoluble. However, I need to scan over to the right in this box and make sure that silver phosphate is not an exception. So I'm double checking on the right, and I don't see anything about silver in here. So indeed, silver phosphate is going to be a solid. So I put a little arrow next to it in my equation. Guys got that? So I'm only checking the exceptions that are directly to the right. So again, I found phosphates in this box. So I'm only checking the exceptions in this box over here. Started on the left though, and then last thing was I checked on the right. Let's do the same thing with sodium nitrate now. In the case of sodium nitrate, we're actually going to find both ions in the table. We find sodium up here, and we find nitrate right below it. Both of those are in the soluble section, which means they're going to be aqueous, unless there's an exception, and you see that for both of these, there's no exceptions. So this is definitely going to be aqueous, dissolved in water. Questions so far? Let's go back to the equation now, and we can fill in that information. Silver phosphate, we found out, forms a solid, so we put an arrow there, and we put an AQ there. It's dissolved. So for the next steps, it's really helpful if we can understand what that means. So I made a diagram up here for you all to think about what that means. So here's the balanced equation that we just came up with. And I drew in all of these participants in the equation, okay? So one thing that's a little bit counterintuitive is all year we've acted like this compound is together. But you might remember in our ionic compounds unit that I mentioned that when you put these ionic compounds in water, they generally separate and dissolve. You guys remember that thing? Okay. So that's what I'm showing here. Anytime you have aqueous compounds, it's a little misleading. The compounds are not actually together. They're not actually dancing like I told you guys they were. They are separated out like this, floating around as individual ions. Only the ones that come together to form the solid, the silver phosphate, actually do anything. And I color-coded those red up here on both sides. So the three silver ions right here, here, and here, combined with the phosphate to form one molecule of silver phosphate. Did any of the blue parts up here actually do anything? No, they just remained separate because they were aqueous on the left and they're aqueous on the right, and so they didn't actually do anything. We're going to call those spectator ions. It's like a spectator at a sporting event. They're not participating, they're just watching. Only the red ones up here participate, and the red ones are going to give us our net ionic equation. So let's go back to the example here, and let's write all that stuff out. So as I said, only the silver and phosphate actually do anything, so that's going to give me my net ionic equation. I'm going to have 3 silvers with a +1 charge, and they're aqueous to start with. And they're going to react with 1 phosphate with a -3 charge, and it's also aqueous. And they're going to form 1 molecule of silver phosphate that is solid. And it doesn't have a charge because it's a compound and it's neutral. All compounds have a neutral charge. So that is the only thing that really happens in this particular reaction. All the other components in the equation that we wrote do nothing. They just sit there and spectate. So those are the spectator ions, and they are, I'll make these red, they are sodium with a +1 charge and nitrate with a -1 charge. And those are both aqueous. They start aqueous and they stay aqueous. And that's all you write for the spectator ions. Oh, and we do need to put the ratio in there. So we've got 3 sodiums for every 3 nitrates. Now, in this case, you could put 3 to 3 like I did up here, or you could just say 1 to 1 because those are technically the same ratio. 3 to 3 is the same as 1 to 1. All right. Any questions about that first example? Yes.
How do you know which ones are the net ionic equation versus the spectator?
So the net ionic equation is only the ions that form the solid. So when we look at the compound here, silver phosphate, those are the only ions, the silver and the phosphate, that did anything. The ones that stayed aqueous didn't do anything. So in the net equation, we only put the ones that form the solid in there, those components. Make sense? Okay. All right, give the U try a try. All right, I already did steps 1 through 3 for you because we should be getting pretty comfortable with those. So we have a balanced equation. You guys have any questions about what I did up there for steps 1 through 3? Okay. So the net ionic equation. Here's one way to think about the net ionic equation. Make sure I leave enough space here. We're always going to have 2 aqueous things forming a solid thing. Does that make sense? So we're always going to have that for the net ionic equation. And down here, we're always just going to have 2 aqueous things that don't do anything except stay dissolved in water. All right? So let's look up at our equation now. And we got to figure out which of these compounds would be solid. So we're going to go, and we got calcium carbonate and lithium bromide. So we're going to go to our solubility table here. And I'm not going to look at the right until I find what I'm looking for on the left. So the things I'm looking at are copper. Was it copper carbonate? Okay, copper carbonate. And what was the other one? Lithium bromide. So copper carbonate, I start on the left and I scan for either copper or carbonate. I don't think you're going to find copper anywhere there, but I do find carbonate right there in the insoluble section. So it's going to be insoluble unless I find an exception for copper to the right. Do I find an exception for copper in here? I do not. So it's going to be soluble. I'm sorry, insoluble. So I'm going to put a downward arrow in the equation. Lithium bromide, on the other hand, I find that in two places. I find lithium up here in the soluble section, and there's no exceptions. And I find bromide in the same section, and again, there's no exceptions. Once you figure out one of the ions in the compound, you don't have to check the other. I'm just kind of proving to you guys that they're always going to agree with each other. They're never going to contradict each other. So we didn't have to find bromide up here once we found lithium. Make sense? So this is going to be aqueous. So let's go back to the equation now. And we can fill this in. This is our solid. This is our aqueous. So the net ionic equation is going to be those parts that formed the solid only. It's going to be the copper and the carbonate. So let's write that in here. We have Cu plus 2, and I just have one of those. And then I have carbonate minus 2, again, 1-to-1 ratio, and they form copper carbonate. Questions about that? Yes, sir.
Do you have to write the charges?
You do have to write the charges because we're showing that these ions are floating around dissolved, and when they're dissolved by themselves, they have a charge. So we want to show that. When they combine with each other, they lose that charge because they become neutral in the compound. Okay, the spectator ions, that's everything else from the equation that didn't do anything. That would be the lithium plus 1, and I've got 2 of those, and the bromide minus 1, and I've got 2 of those. Again, if you want to put that as a 1-to-1 ratio, that's fine with me. It really is a 1-to-1 ratio, but 2-to-2 is fine. And I should separate these by a plus sign. Plus sign is a little misleading, though, because it kind of implies that something is happening. It's just to show that we have 2 separate things here that are spectating. Any questions about that? Okay, give the practice problems a try on pages 48 and 49. The equations have already been balanced for you, so you're just focusing on steps 4 and 5 today.